Hey everyone, my name is Bharath. I am currently working as senior Salesforce consultant with over 9 years of experience in Salesforce and cloud technologies. Over these many years, I have delivered Salesforce implementations, cloud integrations, and AI-driven solutions across industries such as finance, healthcare, and real estate. In today's session, I will walk you through the topic, architecting AI native platforms. This talk will focus on how infrastructure workloads and governance come together to make AI work at scale. We will also look at real world implementation patterns and future trends. By the end of this session, you will have a clear understanding of the challenges, best practices, and takeaways for building scalable AI native platforms. The infrastructure imperative. The starting point for AI initiative is infrastructure. Without the right infrastructure, most AI projects remain in experimental phases and fail to reach production. AI requires compute intensive GPUs, high performance networking, and scalable storage. There are two risks to highlight here. First, organization that embrace infrastructure can achieve a competitive advantage, deploying AI models faster and more reliably. Second, those that focus on experiments without production ready infrastructure fall into what I call the experimental trap. This means AI never scales beyond pilots. So the message is clear. Treat infrastructure as the foundation of your AI journey. Understanding AI workload characteristics. AI workloads are very different from traditional applications. Training workloads require massive parallel processing, where GPU shine. Inference workloads, on the other hand, focus on speed and scalability. Think of recommendation engines, chatbots, and fraud detection models. They need millisecond responses. This means infrastructure must consider both sides, training environments that are compute heavy and inference environments that are lightweight but scalable. If we don't understand workload characteristics, we risk over provisioning, underutilization, and spiraling cost. Data pipeline. Data is the fuel of AI. Without well structured and governed data pipelines, even the most sophisticated models will fail. A robust data pipeline ensures data is collected, cleaned, transformed, and served consistently. Future stores are becoming a critical component. They allow teams to reuse features across models and ensure data consistency. Stream processing adds another dimension, real-time insights. For example, in fraud detection, if data pipelines lag, even by a few seconds, the opportunity to stop fraud is lost. Infrastructure patterns for scalable model training. Scaling model training is not trivial. We face challenges in resource management, container isolation, and network topology. And container orchestration solve many of these challenges. But GPU scheduling, network optimization, and distributed training strategies are equally important. For example, let's say distributed data parallelism allow us to train large models across the multiple GPUs. Fault tolerance mechanism ensure that even if one node fail, training continues to see resource management challenges. Resources is a balancing act. The key challenges include allocating GPU and CPU resources effectively, isolating workloads through containerization, designing network topologies that support high data, building system resilient to hardware failure. If resource management is not handled properly, costs skyrocket and innovation slows. That's why AI native platforms must embed resource governance from day one. GPU and CPU optimization. AI workloads often involve a mix of CPUs and GPUs. CPUs are great for general purposes tasks, while GPUs accelerate matrix heavy computations in model training and inference. The challenge is in optimizing utilization of both. Heterogeneous resources scheduling ensures that workload are directed to the right compute layer. This improves efficiency and lowers cost. For instance, lightweight processing may run on CPUs, while the heavy model training runs on GPUs. Data pipeline architectures. Modern AI platforms rely on advanced data pipelines. A future store ensure that right data is consistently available for training and inference. Stream processing handles real-time data, allowing systems to react immediately. The architecture must balance batch and real-time processing. Batch pipelines are great for large historical data sets, while stream pipelines ensure responsiveness. Together, they provide a comprehensive backbone for AI native platforms. Observability and monitoring for AI. Unlike traditional systems, AI platform requires observability and multiple levels, infrastructure, data, and models. We need to monitor GPU utilization, pipeline health, and most importantly, model performance. Metrics such as accuracy, precision, recall, fairness indicator must be continuously tracked. Observability helps us detect data drift, bias, and performance degradation early, preventing the costly failures. Real world implementation patterns. AI native platform looks very different across industries. Some examples. High frequency trading, it requires ultra low latency infrastructure and real time pipelines. Content recommendation, it needs scalable system that personalize at the individual level. Healthcare AI, it particularly focuses on compliance, accuracy, and ethical safeguards. These industry specific examples remind us that there is no one size fits at the level of AI platform. Architecture must align with business goals and compliance needs. Performance optimization. Performance optimization is about making sure resources are used efficiently. This involves optimizing GPU memory usage, improving storage performance with NVM, and tuning model serving layers to reduce latency. For example, batching interface request can reduce overhead, while caching frequently accessed features improve. Small optimizations at scale create massive performance gains. Security and governance in AI platforms. In AI platforms, cannot succeed without robust security and governance. These include protecting models from adversarial attacks, ensuring data privacy, and implementing role-based access. Governance also means ethical oversight, making sure AI decisions are transparent, explainable, and compliant with regulations such as GDPR and HIPAA. Future trends in AI infrastructure. Looking ahead, several trends will shape AI native platforms. Edge AI, bringing intelligence closer to the source of data. Quantum computing, unlocking optimization problems traditional hardware struggles with. Neuromorphic computing, mimicking the human brain for efficiency. Automated ML and explainable AI, democratizing AI while keeping it transparent. These trends will transform the way we think about scale and adoption, building the roadmap for the foundation of AI-driven innovation. Implement AI native platforms successfully. Organizations particularly need a roadmap. These include short-term wins such as building feature stores, medium-term goals like integrate observable, and long-term strategies like adopting edge or quantum computing. The roadmap should balance innovation with governance, ensuring sustainable AI. Key takeaways and the conclusion. Protecting AI native platform is about uniting infrastructure, workloads, and governance. Here are the key takeaways. Infrastructure is the foundation of scalable AI. Understanding workload characteristics for effective design. Data pipelines are the backbone of reliable AI. Observability ensures continuous improvement. Governance builds trust and confidence. Future trends demand ongoing innovation. Thank you for joining this session. I hope this helps you strategically about building a native platform. Thank you.